always.
Calculator we use
There's a lot of us like to do a hot camera like that.
Then you come next class and you do it. Okay. We don't change assessment times for individual students because then it never happens.
What if you're one of those students who always brings in a calculator and you...
Okay, if you don't bring a calculator, you're getting an after-school detention, so bring your calculator. It's very simple. Every assessment to science, bring your calculator. Okay? Very, very simple. Okay? Not you bring a pen, you bring your pencil case, have the calculator in it. That will make it simple. Right, let's go. Now we started originally, now for that particular slideshow, that first one, people wasting time, 5, 6, 7, 10, 11, 13, 15 to 18 are the key slides. So it's quite busy. It's quite a full slideshow. But these other ones, these are quite short. That one there, hydrocarbons, obviously quite a large slideshow, quite a few things being covered. Right, so for that first slideshow, we are looking, there are your key learning intentions, but in terms of slides, slide 5, what do atoms want? Okay, this idea to have a valence shell like that of the nearest noble gas. Okay, so to have, ideally, 8 valence electrons. Now, in year 9, you looked at ionic bonding, where you have electron donors and electron acceptors. And on your periodic table, I had you, who's got a periodic table here?
Yeah.
Quick, show me a periodic table. You should have notes on your periodic table to show that groups 1, 2, there are notes for year 9 on the back already. No, you're not bringing, you're not bringing this in. You have a periodic table will be given to you. A valency table, not a valency table, a reactivity series or an activity series will be given to you, but that's it. The periodic table will look just like that. You need to fill in the jigger, you need to fill in any notes that you want to. You should know which of these groups are the electron donors, which of these groups are the electron acceptors for ionic bonding. So groups 1, 2 and 3, electron donors, 4 are 5, 6 and 7, electron acceptors for ionic bonding. You should also, there's a few things missing here, in terms of, more reactive, so most reactive down this corner, least reactive in the top right corner, and then noble gases over here, and the octet rule should be marked. I'll send you out, that is your last warning. Okay, and then of course, we'll talk about covalent bonding as well. Yes?
On the slide, does it say like which ones, which groups share? Like, yeah.
We went through that. Certainly it's on the video, there's no doubt about that, because we worked through it on the periodic table. But on the back of that sheet, it tells you, what does it say on the back of that sheet, up the top here, groups, let's see, groups 1, 2 and 3 donate 1, 2 and 3 electrons.
Yep.
Group 5, 6 and 7 accept 3, 2 and 1 electrons for ionic bonds. Okay, that is all there. So you need, that is revision by the way, from year 9. So that idea with an ionic bond where you have electron transfer and then electrostatic attraction where things stick together. So that was all revision from year 9. Obviously you should recognise that if you're, that's a key slide there, right there. If it's got that C for cram card, it's absolutely key. The periods go across the periodic table and they represent the shells being filled. The first period is the K shell being filled. The K shell can hold 2 electrons. The second period is the L shell being filled, can hold 8 electrons. The third period is the M shell being filled, can hold 18, but 8 by the time you get over here is where it wants to be in that third shell. Yes?
Which slide should this?
That's the first one. Okay, it is called Review Electron Bonding 2017. Yes?
Do we only do K, L, and M?
Yes.
Okay. What happens if they find a new element? They just like add it at the bottom, or is it?
It depends on the number of protons. Lachlan, I'll get you to move.
Sorry.
No, just move. Yeah, it depends if it's got one valence electron, it's going to be in group 1. Yeah. It doesn't matter how many electron shells it has. If it's got one valence electron, it's in group 1. Yeah, because it'll have the properties of that group because of the valence electrons. And the proton number determines. No, over here on the end. Proton number determines placement. Okay. So, and groups are indicative of valence electrons, the number of electrons in that outer shell. And groups react in the same way because they have the same number of valence electrons. Now that is all revision. You don't need to know that one. There is your ionic bond, electrostatic bond between a metal cation. What does cation mean? Positive ion. And a non-metal anion, a negative ion, producing a salt, which is in a crystal lattice. This configuration. So it doesn't form a molecule. You don't have sodium chloride stuck together and just trotting around like that. And here's another sodium chloride. They actually form large crystals. So you have, there's your sodium, and it attracts a lot of chloride ions. And that chloride attracts a lot of sodium and back forth, and you get this crystal shape built up. So one of the properties of an ionic bond is that you end up with a crystal lattice formation. And you need to be able to discuss ionic versus covalent. You need to be able to contrast ionic versus covalent. So I think down, there's covalent there. I'll just sit there. That's the one where you contrast covalent and ionic, and you need to know that. An ionic is non-metal and a metal. A covalent is a non-metal, non-metal. So if I just give you a look, is that covalent or ionic? Look on your periodic table. It's covalent because hydrogen can act like a metal or a non-metal, but in this case it's acting like a non-metal. And oxygen is definitely a non-metal, so it's a covalent bond. So looking at things, you should be able to tell whether it's an ionic bond or a covalent bond, or if they're feeling whimsical, both.
If that was written the other way around, so like O and then H, would that be ionic?
No.
That isn't.
It's hydrogen still acting like a non-metal bond. And you should already know this. What group is oxygen in? 6. How many valence electrons? How many valence electrons if you're in group 6? How many valence electrons if you're in group 6? 6. If you have 6, how many do you want?
2.
No. How many do you want in your valence shell?
8.
8. Right, so there's oxygen with its 6. Hydrogen has 1 in each case, and in order to get that valence shell configuration, then oxygen is going to share 2 to get 2, and you get this thing happening. Structural diagram showing a covalent bond between hydrogen and oxygen. Okay, and so yes, that is a non-metal bond. They share electrons. There's no electron transfer. No charges. They have positive and negative charges. So the overall water molecule will class as neutral, electrically neutral. Don't worry about naming. That's solid at room temperature, solid, liquid and gas at room temperature. Because low melting and boiling points, high melting and boiling points, and weak attraction. So you've got weak bonds effectively in covalent and strong bonds in ionic. Okay, and I've jumped the gun a little bit there. Let's go back to covalent bonding. When non-metals come together and share electrons. Carbon is in group 4. It has 4 valence electrons. It wants to have 8, and it can achieve that by sharing 4 in order to gain 4 from sharing with hydrogen. So on your periodic table, above your non-metals, you should have recorded which ones are likely to share. So for example, if you're in group 4, a group 4 element like carbon has 4 valence electrons, so it will share how many? Oh, I'm going to make that a bit neater. It's going to share 4 in order to gain 4. If you're in group 5, you have 5 valence electrons. How many will you share? 3. You'll share 3 to gain 3. If you're in group 6, you have 6 valence electrons. How many do you want to share? 2. Share 2 to gain 2. If you're in group 7 and hydrogen, how many do you want to gain? 1. Group 7 want to gain 1 to get to 8, and hydrogen wants to gain 1 to get to 2. So they will share 1 to gain 1. And that information should be on your periodic table for groups 4, 5, 6 and 7. Okay. There's one other thing on your periodic table. I saw a question that mentions alkali metals. That's group 2. Oh, sorry, alkali metals, group 1. Okay, alkali metals, group 1. So you can write that down as well. Okay. Now, there's that. We've been through that. Lastly, on that slideshow, you needed to know the difference between a Bohr diagram, which shows all of the electrons, but in year 10 we're not interested in that. We're interested in valence electrons. So we don't draw Bohr diagrams anymore. You have electronic or electron configuration, which is just the number of electrons. Carbon has 2 in the K shell and 4 in the L shell, so it's got an electron configuration of 2, 4. So you can be asked a question like that. So electron configuration is just a listing in using numbers to show where electrons are. And then for you guys, you need to know Lewis dot. You need to be able to do those. And you need to be and with Lewis dot, obviously lone pairs if you do molecules. So there is water in a Lewis dot diagram. Oxygen in each case is sharing 1 with each hydrogen to gain 1 from each hydrogen. And the lone pairs up there. We've been through that a few times. You need to include them. So you need to be able to do that as a Lewis dot diagram, only showing the valence electrons again. Only showing the valence electrons. Not interested in inner shell electrons. And if you do that as a structural diagram, again, instead of doing the dot dots, which take a lot of time, you use a line to indicate there's 1 electron being shared from oxygen, 1 electron being shared from hydrogen, and then you've got your oxygen lone pairs. And these are the ones that you'll do, especially for hydrocarbons. Structural diagram. Lone pairs must be shown. Any questions about those? Okay. So that's where we are for that. Most of that slideshow is just revision. Then we went into 3D shapes. Do you remember this? Molecules forming 3D shapes. And that key slide is very, very important. Why do things form a bench shape? Why do they form a linear shape? Tetrahedral. You need to know all of these names. You need to know, like from memory. You're not going to get any kind of table or anything like that. There'll maybe be some diagrams, but you should be able to recognise that that's trigonal planar. And you need to know how they form. Okay. Most of the time, the questions in these sorts of assessments involve recognising shapes, not working out shapes. But that can happen, where you get given a formula and you need to work out the shape that it forms. And how do you do that? Remember, okay, well, from VESPA, key point. Valence shell electron repulsion theory. Why do things form 3D shapes? Because the electrons, the valence electrons, repel each other. the negative charges associated with these electron pairs, try to keep them as far away from any other electrons as possible. Okay? So that's the greatest distance. 120 degrees is the greatest distance. This one here, I think, is 109.5. Equally is the greatest distance for a tetrahedral shape. So that's why, in every case, the shape being formed is because of electrons trying to get away from each other, as far away those negative charges as is possible. You don't need to know the degrees. Okay? So that's the key point. Form 3D shapes because of negatively charged valence electrons in the atoms repel each other. Almost guaranteed you're going to get that as a question. Because VESPA, there's only two things. One, why. Two, show me what you know for shapes. Slide 5 is gold. Okay, that's how you do things. Locate the central atom. The central atom is the one with the most bonds, usually carbon. Okay? Then, around the central atom, use a structural diagram. Is easiest. Lewis you can do, but structural is easier. Then, the number of things, atoms or lone pairs around the central atom determines the shape. Okay? So, you have two atoms here and no lone pairs around the carbon. So it's got a 2-0 configuration. And 2-0, if you go here, 2-0, 1-0 or 2-0 will give you linear. Double bonds, that doesn't matter. It's still counted as, it's still counted as a central atom with two things around it. So it's 2-0. 2 meaning two atoms and 0 lone pairs, linear. If you have 3-0 or 2-1, adding up to 3. 3-0, that's 3 atoms and no lone pairs, trigonal planar. 2 atoms and a lone pair, you will never see that one, is bent. If you have 4, a total of 4, which can be 4 atoms for tetrahedral, 3 atoms and a lone pair for trigonal pyramidal, and 2 and 2 is bent. Water is typically something you'll see. And you have drawn all of those. The exercises we did explored every possible shape that you'll get, and you also basically did every year 10 molecule that can be asked. Like carbon dioxide, pretty common one. Okay, I've seen many assessments just give you carbon dioxide and show what is the 3D shape. Yeah, and so your notes are very solid. The worksheet that you did explores that very well. Yes.
Why will we never see bent?
No, you will see bent, but not that one.
Why not?
Because that one isn't following the octet rule, and so we're just going to leave it alone. Okay? So that's the one that you will see. The water one is really common. Any questions about those? That's really it. 3 slides it comes down to. Why things happen, how you go about the methodology, and that particular table. You won't be given that table. You're just not. So you basically have to remember, for these low ones, it's linear. It gets a little more complicated. Up to 3, it's one of those 2. Up to 4, and you can work out the shapes by literally doing the structural diagram and then working it out from there. Okay? But you will need to know all of those names. There's no getting around that. Okay. Now, next, reactivity of metals. We looked at this. And the key point, there's a couple of key points. 1, in nature, you only find things like gold lying around on the ground because it doesn't react. Okay, it's not reactive, and so gold lying outside won't rust, it won't oxidize and rust, it does none of those things. So it's very unreactive, whereas iron is the classic example, will rust because it is reactive, and lithium and potassium are really reactive, so you absolutely will not find a block of lithium lying around outside. But for those substances that are very reactive, they attract in ores of some kind. That's where you find them. So you have to pull them out of that ore to extract them. This is why gold, people have known about it for centuries, because literally you could find it. It's visible right there. But other things, the more reactive the compound, the less likely that people would know about it, because it has to be extracted from ores. Okay. Now that's the first point. The second point is, what type of reaction is this? Displacement reaction, where one reactant is replaced or displaced by another reactant. The more reactive metal displaces the less reactive metal. You will be given an activity series. Do you know what an activity series is? Do you know what it is? That's an activity series. Something like that. You just need to interpret that. You need to know, oh yes, these are unreactive. These are very reactive. And the types of things, reacts vigorously with cold water to form hydrogen gas. So in the presence of water, literally hydrogen gas will be given off and this will be broken down. Reacts with steam, reacts with simple acids, will not dissolve in simple acids, very unreactive. Back to our little equation, our example. So, if given that, you should be able to tell me, using the table, if a reaction is going to occur. You would look at the reactivity series, and you would say, iron is more reactive than copper, so iron can push the copper out of the way and get the sulfate girlfriend, or boyfriend, whichever way you want to read that. Reactive girl, more reactive than this one, and off you go. So the iron will displace the copper, and you'll get copper as a solid, and that solid is deposited on another metal. And the example we have of that is that there. Exactly that equation. Copper sulfate is green, and then you put an iron metal into it, and the iron displaces the copper, and the copper forms as a solid around that iron nail. And that's what's happening there. Any questions at this stage? So those are displacement reactions. What type of reactions are they? Displacement reactions. Yeah, that's their name. And then, as I said, we mentioned just in general here, we talked about reactivity and whatnot. And in the periodic table, this is already on your periodic table. You should know that the more reactive elements are down here, the less reactive elements are up here. Okay? And so the amount of energy needed to steal an electron, the ionisation energy, is very high. High energy needed to steal an electron from here, low energy, low ionisation energy to steal an electron from something down in this corner. Okay. Now, I think I've covered everything. Oh, there is just a good breakdown. That really does break down. Reactive elements versus unreactive elements. Okay, and the history of them. Known about for a very long time, not known about for very long. Okay. Can be found as free elements in nature, never found as free elements in nature. Some examples, and not easily extracted from their ores. So these can be pulled out of their ores very simply. Not much temperature needed. These ones are more difficult to achieve that. Let's have a look. There's that there. Hydrocarbons. Okay, this is a big slideshow. No ifs or buts. And you should know the different groups and the number of bonds that they need to form. Carbon is in group 4, so it wants to form 4 covalent bonds. Now, I've actually changed one of the figures to help you out a bit. That's your index of terms. This is a structural diagram. In some textbooks, they say structural formula. So on your practice test last year, the instruction was draw the structural formula of pentane. And we had the test, we went through the test 2 days ago, and we're going through it again today. And I made sure the wording says structural diagram, 4 diagrams, formula for formulas. Okay, just so it's not very confusing. It doesn't confuse people. So structural diagram is the drawing. The chemical formula is just the count of carbons and hydrogens. These are hydrocarbons. What atoms do we find in hydrocarbons? Hydrogen, carbon. Carbon's in group 4, it forms 4 bonds. Hydrogen's in group 1, it forms 1 bond. Structural formula is just, effectively, you read it from here. So do this first. If you're doing a question, do the structural diagram first, and then you can read the formula off. CH3, CH2, 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 CH3, and then you can condense it. CH3, 3 CH2s, CH3. You won't ever draw those. You sometimes get them and they say, what is this? What is the name of this compound?
Ball and stick model.
For a ball and stick model. And you go, well, that's a carbon, 1, 2, 3, 4, 5 carbons. Methane, ethane, propane, butane, pentane. I only see single bonds, so it's an ane, so it's pentane. Done. Okay. Otherwise it would be pentene or pentine. Now, I changed this because I like you. Who can see the difference?
Oh, I will find it.
Okay.
Do you draw them?
Down the bottom, the covalent bonds. Carbon will form 4, hydrogen will form 1, and oxygen in alcohols will form 2. With lone pairs. If you don't include those, you'll lose a half a mark or a mark. Not sure which. But you need to know that. If nothing else, if you don't memorise anything else but that, that's the thing you really need to get down. Because it has the formulas and it has key terms. What does saturated mean? Only single carbon bonds. There's no double bonds, there's no triple bonds. That's what an alkane is. The formula is CnH2n plus 2. You need to know that. It has an ane ending. So the question can be written from any direction. You can get given a chemical formula and they ask you, is this an alkane, alkene, alkyne? And you have to work it out. Oh yeah, if it's this formula, this formula, this formula. You can be given a name and have to derive the formula or the chemical formula from it. Alkenes, CnH2n, they are unsaturated as are alkynes. Unsaturated means there is at least one double bond or at least one triple bond. This has the maximum number of hydrogens. It's saturated with hydrogens. Okay? This has an ene ending and an ine ending. The number preceding the ene or ine indicates the carbon atom on which the ene double bond or the ine triple bond is found. So but1-ene has the double bond on the first carbon. But2-ene has the double bond between carbon 2 and carbon 3. Now, alcohols have a functional group, OH functional group, the hydroxyl functional group. Butanol has the OH on the first carbon. Butan2-ol has the OH on the second carbon, so there's a naming convention. And these are your covalent bonding structures for all of these. You need to know those prefixes. I told you that day one. They need to be memorised. There's no getting around that. You don't get given those. You should know some properties. For short hydrocarbons, they burn very easily. They're very volatile. Barbecue gas. Long hydrocarbons, think bitumen outside in the road. Don't burst into flames very easily. Take some of the road home tonight. Put it in a pot. Heat it up. See if it will burst into flames. It won't. Don't do that. That would be a bad idea, but it won't. It's very, very stable. The short hydrocarbons are very volatile. Okay? They get soft on a hot day, but they won't burst into flames. Yeah? But barbecue gas is ready to go straight away. And obviously petrol, you're not lighting the liquid of petrol, you're lighting the gas of petrol. We did that as an exercise, and you should be able to do that. You'd be expected to be able to do that. Okay? That's the answers. That is naming, which we just talked about. Okay, so 1-butine. This is the convention we're going to follow. Some textbooks do that, but we're not going to do that. We're going to follow that convention. But1-ene has the double bond on the first carbon. But2-ene has the double bond on the second carbon. And you can come from any direction, either direction. Okay, left to right, right to left. That doesn't matter. Constitutional isomers, you need to be able to draw them. So what are they? Sometimes some books don't use constitutional, they just use isomers. Same chemical or molecular formula, different structural formulas and diagrams. And the diagrams are what you'll be asked to draw. So here is butane, methane, ethane, propane, butane. And here is an isomer of butane. That's the proper name. I don't think you'll be asked for the proper names, but if you get asked, draw 2 isomers of butane, well, that's the first one. That's a gimme, because it just means, you know, you're anything using that formula, anything that is a legal structural diagram using that formula. So the first one's a gimme, straight chain one. The second one doesn't have a straight chain, it's got a kink out the side. And I was going to say a methyl group coming out the side. So 1, 2, 3, 4 carbons as well with your hydrogens fitted in. Okay? You can't draw, this is not a different, this is not an isomer. Because these two are the same. You see why? Yeah. Well, I mean, all I've done is I've just put a bit of a bend in it, but really that is still just a chain of carbons. Okay? It needs to be distinctly different. If you draw things, you have to include the hydrogens. Sometimes in class, just to be fast, I draw the line, but I don't draw the hydrogens. You have to include every single hydrogen, every time. So normally the person who writes the test is quite kind. They'll only have 4 or 5 carbons, not 22, which would be horrible and stressful. So you need to be isomers, be able to work with them, and certainly draw them. Naming them, not so much. And you should know that there's a lot of them, and that's what's coming out of oil wells. Lots and lots and lots of different hydrocarbons. And they need to be sorted. Now, hydrocarbons are obviously used in pharmaceuticals and plastics and things like that. We didn't touch on that very much. Then we looked at alcohols. You have the functional group. So if you get a compound and it has an OH on the end, a hydrocarbon, what is it? It's an alcohol. As soon as you see the OH, alcohol. Straight away. So it's no longer butane, it's butanol. Okay? And that's the hydroxyl group that defines an alcohol. So that's methane, ethane, methane, ethane.
Hydroxyl.
That one?
Huh?
What?
Don't.
Okay. Methane, ethane. That would be ethane with just like that, but ethanol with the OH on the end. Now, in terms of drawing these,
When we get our test?
that's a prac, but not until everyone's done it. And that's everyone in the Year 10 cohort. Okay, now, a few mistakes that people made. He says, going Soto voice. We went through this in class. Number of carbons. This is a combustion reaction. So this has got heat coming out. Heat and light. Yes? This is what you're warming your hands with. So, but the number of carbons is the same. The number of hydrogens on both sides is the same. How many atoms are destroyed?
No.
0. So if you were writing in your prac about carbons being burned during combustion of alcohols, no. Where does the energy come from in this reaction? This is like heat and light are coming off. Where is the energy coming from?
The break.
The breaking of bonds. High energy bonds on this side, low energy bonds on this side. And that energy is what you're feeling as radiant heat and seeing as light. High energy bonds on the left, low energy products on the products with low energy bonds here, reactants with high energy bonds here. And that's what's happening. You need to be clear on that. Okay. And so, obviously, now, just quickly, knowing this, this is ethane, this is ethanol. Which one has more energy per gram? Hey, wake up. This is ethane, this is ethanol. Which has more energy per gram? Ethanol, why? Does it have an extra hydrogen? No. This has 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Oh, that's not true. Who left those there? 6. 6 hydrogens. 6 hydrogens. 2 carbons, 2 carbons. But that has an oxygen. So, what's that oxygen got to do with anything? It has more bonds. Count them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8.
You missed the
I don't think I did.
You just
It's dead.
You counted one twice.
1, 2, 3,
Count the other
4,
one.
You still
5,
counted
6,
You
7,
counted-
8, 9.
Oh, man,
Oh yeah, 8.
he's trying his best.
That's 8. 1, 2, 3, 4, 5, 6. Is that 8? 1, 2, 3, 4,
No.
He's having a crack, we'll let him on.
5, 6, 7, 8.
Top one and 7.
Fine.
Cut him
Still,
being a teacher.
the point remains well spotted. Extra bond. So that's what it comes down to, and that's what your prac, 2 of the main questions were asking. And if you started talking about carbons burning, and there's more carbon to burn, you are fundamentally wrong. Okay? Because it's purely comes down to bond energies. High energy to low energy products. And you have more bonds, you get more energy. That's it. Okay. Let's have a look. Now. Yes. A few people got that wrong. In your prac, when you draw these alcohols, what do you include?
Like hairs.
Every time. A lot of people, and to be honest, the original slide, it just said OH, and I remade it just to make it clearer for people. You have to include those in your structural diagrams. And that is pentan 2-ol because it has the second carbon. That is the second carbon. I'm reading that way. An OH group. This is the third carbon has the OH group. And so it's pentan 3-ol. I had to do that. And lastly, there's 2 things. Fractional distillation. Distillation is this idea that you can separate things. How do you separate things using distillation? What's the key thing? Boiling points. Different boiling points allow you to separate things in solution. And so this, by the way, in your notes, I did not say that this is called a fractionating column. But in the test, the term fractionating column is used. So the name of that object is a fractionating column. If you want to put in your notes, fractionating column. And I always spell column wrong, and I probably spelled it wrong there. I've misremembered it perfectly 10,000 times. So I have a perfect memory for misspelling. Now, with that column, is it 1L? Yeah. In that column, you should understand which products get to the very top of the column. No. You still got time.
The hottest one.
8 minutes. It's yours to use. You're handing it in. Did you hear the same question? Too good. No, there is no.
Frank.
Hang on.
Release the ninjas. You don't get that. Release the
Stop talking right now.
Dylan's in the room over there. I'll watch Dylan.
Great counsel about that. I'll give you some extra.
Really?
Because you went there.
I usually
Put your hand up.
Yeah, they're right.
Okay. So, listen up, let's finish. That that fractionating column, the short chain carbons, Grace, the short chain carbons reach the top of the column. And the longer the chain, the further down condensation and then collection occurs.
Do we have to
Now you don't need to be able to draw that, you need to understand it. Okay, guys talking at the back.
I do apologise.
You need to understand that the longer the chain, the further down collection occurs. So these are the very long chain carbons, C20s all the way up C60, C80, whatever it might be, is collected as residue. And so this difference is based purely upon boiling point. Okay? So the ones up here have high boiling points or low boiling points? Low boiling points, high boiling points. Low boiling points, high boiling points. And there's a second picture there that can help you with that. And the last thing we do is combustion reactions.
Can we check?
No. Last thing we do is combustion reactions, and long story short, you don't need to balance these, that will come later, but you need to recognise them. So in complete combustion, what are the products? In a complete combustion reaction, what are the products? There's reactants and then there's products. Sorry, what?
Carbon monoxide.
This is complete. Carbon dioxide and water. Complete combustion has carbon dioxide and water. Now, what about incomplete combustion, which is less oxygen available for combustion? For incomplete combustion, what are the products? Carbon monoxide, and it's always carbon monoxide, and it's always water, and sometimes carbon as soot. So, let's have a look at this. For these ones, listen up. Water is always formed in combustion. So, if you're asked for products and you put water, you'll be given no marks. If they say, compare complete combustion and incomplete combustion, and you say, in incomplete combustion, water is a product, you will be given no marks, because it's also incomplete. During complete combustion, you also get water. So water is common to all three. But instead of carbon dioxide, you have carbon monoxide in both cases. And sometimes you have carbon as a solid, which is soot, okay, which is the ashes that you see. So you don't need to balance equations. You do need to recognise these products, and the difference between complete and incomplete combustion is the availability of oxygen. Any questions there? Okay.
So
Yep.
complete combustion has like basically two
No. Complete combustion has plentiful oxygen, so that the reaction, the products are carbon dioxide and water.
So incomplete combustion is monoxide, it's like one.
Yes.
Just one.
Yes. Done. Still talking.
No one's talking.